mode here. All right, so thank you for that introduction and the opportunity to present at ASCE. Just a brief background about myself. I'm a staff engineer at the Idaho Transportation Department in the North Central Region, District 2, based out of Lewiston, Idaho. I've worked for the past 7 years as a project manager in design construction and recently became the District 2 materials engineer, but stepped in as the project manager for the rockslide project. I've had the pleasure of working with the Bill Gates and introduce himself.
Thanks, Janet. So I've been involved in this project ever since Brian Bannon gave me a call about 8 years ago when we had the initial rock slide. My background, I'm a retired Army officer. I spent 22 years in the military, both in Special Forces. They sent me back to undergraduate school for a degree in geology, sent me back to graduate school for a degree in engineering. And so I've been messing around doing this stuff for a variety of different things for about 50 years. Learned a lot of my initial blasting demolitions from the Army when I was in Special Forces there. And then I actually took a construction blasting course from Jerry Wallace about 20 years ago, and we've been working together on since then. So with that, we'll get into the presentation.
All right, so I just want to take a minute before we talk about the project to recognize the collaborations and partnerships that made this project successful. From the initial slide on July 3rd to May, we couldn't have done it without the hard work of all the folks on the screen. And I apologize if I missed anyone, kind of ran out of space, but thank you all for working on it. We wouldn't have been able to do it without cooperation. So as Lauren mentioned, we had a slide on July 3rd. About 10,000 cubic yards fell down at 9 a.m. And I'll show you a vicinity map, kind of roughly where that occurred if you aren't familiar. But first, I wanted to show a video. It's amazing that the traveling public was able to capture this video. No one was hurt. It kind of gives you an idea of the risks and of this corridor.
Oh my gosh. Jesus. Oh crap. This is not going to come.
That's the understatement of the year there.
So thankfully, on the July 3rd slide, and we'll talk about the July 10th as well, nobody was hurt, and that's pretty incredible footage of that slide. So in case you aren't familiar, the blue arrow shows just 7 miles south of Riggins at milepost 188. It's where the occurred. And I just showed the route getting from Boise up to Lewiston because that's where I'd be traveling, but most folks might be traveling further north up to Moscow or Coeur d'Alene. And obviously this is a terrible weekend, not that there ever is a good one, but a lot of folks are planning recreation activities, visiting family for the 4th of July. And that's a critical route, the only highway north-south in Idaho. And so I just showed one detour possibility, and obviously it depends on your configuration, but you'd have to go up through Oregon, Washington, or through Montana to be able to get to northern Idaho. And just for some perspective, there's about 2,500 vehicles per day that travel this section of road, and 18% of that is commercial traffic. So before we get into the response, and obviously it was a very critical route to get reopened, Bill's going to give us an overview of the history of failure at this location.
Thanks, Janet. So what we have here is it's a metamorphic intrusion, basically composed of a greenstone that is typically called serpentinite or serpentine type rock, and it's interspersed with about 4 shear zones. Along those shear zones, you'll find a schistose type rock and such. And this rock's outcrop is about 250 feet high, about 800 feet long. And actually, they've had a history of rock slides here all the way back to when they pushed the road over on this side in the early 60s. In fact, during the scaling, we found an old detonator up on the rock slope that Jerry had dated back to early 60s, which makes sense. This is when they were initially working on the slide and such. And so back in December 2012, I was actually scheduled to give a blasting class to the District 2, and Brian Bannon gave me a call and said, oh, by the way, can you come over early? We just had a rock slide on 95 that closed the highway. And so I immediately got a hold of Jamie Schick, who is one of my colleagues that have been working on this slide since then. And we went over to take a look at the rock slide. So what you see on the left is our initial evaluation of the rock outcrop. To your left is north, and you'll see that line that comes from the skyline down. The first rock slide occurred there, about 10,000 cubic yards, slid down and blocked the highway. So Jamie and I got up on ropes and started looking at the rock slide, or the rock mass itself, and we're able to identify actually about at least 4 distinct blocks. We labeled block A through block D. The big problem was block A was destabilized from the slide and was leaning back from the rock slope about 8 feet, and we had a tension fracture underneath it. Went back underneath the rock mass probably 40 feet or so. And so we initially came up with a mitigation plan to shoot that block off, which we did, and then evaluated the rest of the rock mass. And so we got back to ITD the next day, driving like mad. I was driving, Jamie was putting the slides together on PowerPoint as we drove down the road, and briefed the engineers here at District 2 what the problem was. Basically, we saw a tension fracture that went from block A across the top of block B down to block D that was gaping open, and we were concerned that we'd have more failures. And so what ITD did under Brian's direction is put on monitoring points on the rock mass and put some plastic accelerometers made out of PVC across that fracture zone. So the question is, what triggered the slide? Well, there's a couple things can trigger the slide. We're about 80 miles from Stanley, where we've had a history of seismic events over the years, but we have no evidence really that that's caused the failure. Typically in the Riggins Valley there along the little Salmon River, we have some pretty major diurnal changes throughout the day and throughout the season, where you'll have the freeze-thaw events and then just the heat and cooling of the rock mass, which can tend to loosen up and cause rattling, sometimes rockfall. In addition, we have, if you look at the right picture, July 10, you can see water that's coming out from below that upper rock mass. And that was indeed, just after that failure, we could see water there for a little while and such. And so just the increase in hydrostatic pressures will cause these blocks to destabilize. If you imagine you have this big rock mass sitting on this slide plane that you see that's really open on the right. So you're building up this strain with all this weight of rock and such, and as the strain gets more and more, just like an earthquake, also pop, it releases it, and then you have this big stress relief, and down comes the rock slide. Well, basically, that's what happened. We can't point to anything specifically. It's just, gravity rules. And so you look at the middle picture is I get a call from Brian. Actually, I was out on the golf course on the 3rd July, and he said he sent some pictures. I immediately called him on morning of the 4th, about 6 in the morning, and he said, we just had a rock slide, that lower part broke loose. So you can see that part of block C fell down on the road, blocked the highway again. That's what that young lady was taking a picture of. We still have a little bit hanging up there. And so this is the July 4th of July. I'm trying to get my crew together. Fortunately, all my crew have go bags, and they've gone through all the rope access safety courses and stuff. They're ready to move, and so we were able to mobilize people on the 5th, and we're up to July to evaluate the problem. On the right is the event that happened on July 10. You're going to see these a couple other times because we'll talk about them a little more in detail. But my big question was, when I was sitting there on the reports on July the 10th was I was just kind of curious when the next rock mass was going to come down, and Doral Huff gave me a call and said, "Oh, by the way, that the rock mass that you were looking at on Monday just came down, and fortunately nobody was hurt." Next slide.
So thank you for that overview, Bill. So ITD's initial response on July 3rd was obviously to set up barricades to this area. We'll talk about kind of the challenges it posed later on, but doesn't have any reception. And so it was important to let people know early before they got down to Riggins in an area with limited connectivity that the road was closed. We also faced the challenge of rounding up folks over 4th of July weekend to get operators out all over the region to start looking at the debris and formulating a plan. But one thing that we had to do before we could start the work is make sure that we could do it safely. And that was critical, getting McMillen Jacobs out to be able to assess the slope. We also mobilized David Evans and Associates to put targets on the slope and begin a monitoring regimen. We had ITD spotters out 24/7 to watch the slope and make sure once we got operators lined up and construction happening that we could do it safely. So here's some pictures of that work. Once McMillen had assessed the slope, that we brought in 4 Connex containers that were 40 feet long. We used those to create a protective berm and opened a chute fly that was just 1 lane. It was ready on July 5th, but we still were getting comfortable with the slope, assessing the information that we had available. And so we waited to open to just one-way traffic during daylight hours until July 8th. And then as Bill hinted at, we started to see some movement. So we closed the road on July 9th, but we'll talk a little bit more about that later.
So initially on July 5, actually Brian got they had a crew that was already on contract, TripTech, to come out and do some scaling. So we got on the slope with TripTech on July 5, or correction, July 6, and started evaluating the slope. So basically right now what we're doing is safety scaling, getting some of the major loose boulders and stuff off of there so we can safely evaluate the slope and also get traffic moving. So during the on the July 6th when we got out there, you can see they got the Connex container set up, and they've got that shoe fly operating. And one of the key things is when we got out there, I had ITD start opening up the ditch between the toe of the slope and that berm so we could have a bigger catchment zone. And you can see Jamie and I up there standing on the footwall below the tension fracture. Obviously we're on ropes, so it's kind of spooky out there still. We're looking at that tension fracture. Right there, it's about 5 feet wide. Now, if you look on the right where it says tension fracture, that it stretches from the left, which is about 8 feet open, about 100 feet over to the right to that subvertical fracture. It's about 6 inches wide there and such. And so you can see right below to the left of the arrow, there's a white extensometer there. This is PVC pipe that was basically taped together and some numbers put on there just to watch what was going on. So between what we additionally did is put some additional survey targets on the rock mass itself, and DEA was standing basically down to the left of the Connex container shooting these targets for movement and such. And we're also evaluating the extensometers themselves. What happened was during that period there of July 8th, we got traffic moving. We started seeing additional increase in movement on the surveyed targets, and also the tape broke on the extensometers. I had them re-tape the thing, and then I get a call that evening that it broke again. And so after discussion with Brian and Doral, I said we need to close the road. So they sometimes wonder whether you're going to be a goat or a hero when you close a major artery as such. Fortunately, after we closed the road, it did fail on July 10, and fortunately nobody was hurt. But you'll notice those Conex containers look like tin cans. You just kind of mashed them with your foot. Now, one big block is probably block D that we labeled earlier up there, that big block D, and we got block B's were actually broke down into 3, but it broke all the way along that tension fracture. You see where that PVC extensometer, that one above B3 is the one that broke twice on us. That's when we decided, it's time to stop traffic and get this figured out.
So here's another view of that July 10th slide. The locals called this house rock because it was the size of a house. It was about 42 feet wide, 50 feet long, and an average of 23 feet tall. And the average weight was about, or I guess the weight was 3,500 tons. So that was a significant, we just knew it was going to be a significant effort to clear the road and reopen the shoe fly.
Yeah, that big block you see, house block, is actually probably block D. And you look at those Conex containers, just mashed them like some big giant walked over them.
So another unique thing about the project is typically you don't look for a detour because of a rock slide and address a landslide, but that's what we had to do here on Pollock Road. And so Pollock Road had been closed for several years because of a landslide, and you can see in the picture below that's really not traversable. And unfortunately, Google had this identified as a feasible detour. Thankfully, most folks in this area don't have reception, but we notified Google to take it down until we had made repairs and opened it officially as a detour on July 9th. We worked with the local community because this is a quiet road that previously had been closed. That now was accommodating highway traffic. So it was opened only to daylight traffic, and we shifted those hours based on the needs of commuters and traffic demands in that area. So you can see the shoe fly was open on July 27th. You might have seen blasting videos from clearing the rock and the debris. This time, instead of bringing in Conex containers, we built up a berm like Bill discussed before. This time we had a lot more material, so it was a lot bigger, and beefed up the shoe fly so that it was able to accommodate 2-lane traffic. At the beginning, while we were still developing and making sure that the slope was stable and had relaxed, we only opened it to daytime travel. And we'll talk about nighttime monitoring.
One of the key things is that berm. So I had them working on both ends to increase the size of that berm and open up the catchment zone between the toe of the slope and that berm, because it was critical to catch a rock, not only during when we were preparing to take that large rock mass out of the mouth of that chute, but we eventually we're going to also be scaling that slope, and it works as a good method to capture that rock. Now, what Janet was talking about, the big thing is during we installed additional targets on the rock mass, but we also had monitoring 24/7, watching the slope. We moved all our survey points across the river so we could look right straight across at it out of harm's way. And at night, you say, well, what's good is it watching at night? Well, actually, with those lights, if you have any rockfall, it'll set up a dust storm and it'll look like a big cloud or starburst, and you can really see it. And also, it's quite eerie because you can hear the rock start to roll a little bit and such like this. So we had people sitting up there for the full night just watching this slope.
And we implemented an emergency protocol, and we had that in place earlier, but here's a good time to talk about it. Just so if our spotters saw anything at night, they could reach out to McMillen Jacobs folks and have them assess the slope. If it was critical to do an emergency closure, we had our traffic control company on call 24/7 to do that, put up a posting on 511. And so having all these safety measures in place just made it possible to open the highway back up.
So one of the key things is we have that large rock mass up there. That's 14,000 cubic yards, about 33,000 tons, basically. And we're going to be putting machinery on that outcrop. We're also going to be putting personnel. And so we were very concerned about monitoring movement. You know, we could watch the extensometers that we had on there and physically watch it and look at the surveys, but we felt we needed some more detailed monitoring. And so we contacted BDI, who actually does telemetry on bridges, and say, hey, we got this large rock block. How would you like to try it on this large rock block? And so they brought over their total station system with their rangefinder and such. And we took the instruments they had, and you can see on the slope, we spent a week actually installing both crack gauges. On the left, we were putting crack gauges across between the major block and the slide plane. We're also installed tilt meters. We're putting tilt meters on the right side. We've put prisms on top of the slope right at the brow. And then we pushed additional targets, like you see on the right of that slide down there, that black and white, that's one of the targets that DA would shoot with their total station system. And we put new extensometers across some specific fractures that we were concerned about. The extensometers this time is I had them take a PVC pipe and then put another one inside of it. So the telescope, the one inside of it would paint red, and if when it pulled out and we saw red, it meant stop and evaluate the slope. You could see that actually from across the site at our survey site. So what we have here is our survey site. We're about 5 feet across the river, right in front of that block, the main mast. We're concerned about that main mast that's plugging the mouth of that wedge. And we put in about 20 instruments on it. Now, each one of these instruments is radio controlled, and so it would send a signal by a cell phone to a satellite. These would be consolidated, shoot it to a repeater, and then that would be transferred. We'd pick it up on our computer and also pick it up on our cell phones. And so we would these would be updated every 20 minutes. And so every hour we'd we'd go through all instruments. We'd check all physical surveying. We'd check the extensometers and stuff. And just if we had anything that went astray on any of these, we'd immediately stop and evaluate the problem. The interesting thing is these would measure up to 1,000th of a foot, and you could watch the actual rock breathe during the day. As it got hot, you'd have changes in the movement of the extensometers and actually in the tilt meters primarily, and then they'd settle back down and such. One of the key things was the communication, is tying these into a cell phone. Now, Janet was able to get to Verizon with Verizon. Verizon volunteered to bring out this repeater station at the on loan, with the understanding that we had some major fires going on in McCall and up in the Payette Wilderness area and stuff, that it may be diverted to a fire. And so this was working great for all the way up to about 24 hours before that shot. And Jerry and I were talking with Janet and Doral on cell. All of a sudden, bloop, there it went, and they were moving they moved the repeater. And so Jim Struthers used his ingenuity and it was able to work with Superior, and we got it with their system that controlled traffic lights, and we're back online in about 2 hours there to continue the monitoring. Because the beauty of the telemetry, we could run this 24 hours through the night, whereas the total station of the daylight was only daylight shots, and so this was just 24 hours.
And the nice thing too, I guess, for assurances and opening the road, not for you guys, whenever data wasn't received, the McMillen Jacobs crew would receive text message alerts notifying that there was a problem, that data wasn't being sent from the slope. So there were just multiple security measures to make sure that we actively were monitoring the slope. This is a picture from the top of the slide looking down on the drill rig. So kind of alongside implementing all these safety protocols to be able to successfully and safely do the work for the contract, we were putting together the plans and provisions and specifications for the slide mitigation project. So the PS&E package was ready for advertisement on July 24th. And just a reminder, the original slide occurred on July 3rd. But it's a pretty incredible time for the team to come together and put together a package for bid. It wasn't awarded until July 17th. We held the contract after our pre-bid meeting on July 28th to finish up the details and make available the blasting plan to the bidders. It had critical information about the character of how the rock would come down, which would be essential to their bid. And then we wanted to do a little bit more assessment of naturally occurring asbestos, which we'll talk about a little bit later on, just so that folks could refine their bids.
One of the key things to look at here, you'll notice we got 2 drill rigs sitting on the rock slope itself, on the mass, and we have the excavators carving a trail right now basically along where the tension fracture is. And so because of this, we were very concerned about movement with personnel and the rig sitting on there. And so this is the reason we spent $60,000 just in telemetry alone. One of the key things also is when we started evaluating this is I put together a conceptual blast design and got with Jerry Wallace. Jerry Wallace had been working together for probably 20 years. He had worked on a similar problem with Washtenaw on a block over by Randall, Washington. And between the two of us, I was a blasting consultant, he was a blaster in charge. We started developing a blast plan immediately. This was different than typically, because typically your contractor will have a subcontractor, will have the blaster and the drillers and stuff. In this case, they had the drillers who was Rhino Works out of McCall doing the drilling, and then Jerry was charged. He was the blaster in charge of the project and stuff. So it worked out very well after we got through a couple of rough spots there.
And I think I forgot to say it, but the contract was awarded on August 17th to Scarcella Brothers for $3 million. Like Bill said, it was unique that we had a separate blaster in charge and a separate blast plan. And that saved us a lot of time that we were able to just get in and start drilling within 3 days. The contract had a requirement that the contractor and their subs had to mow bin within 48 hours of the contract being awarded. And we would have started sooner, but they had to pioneer a road down to be able to assess the slope. So 3 days really was the best that we could have possibly done. The first blast was on August 28th, and the final blast was on September 22nd. And overall, the project is planned for completion mid-November. And so it might feel like what's taking so long, but there are a lot of critical pieces that had to come together to be able to do the project safely.
So let's take a look at that block up there. That was a critical block to bring down. Now, there were suggestions, well, you need to bring it down in stages, in lifts, maybe 20 feet thick lifts and stuff. Well, we felt after Jerry and I looked at it, it was just too dangerous to bring down in lifts, that we had to bring it down in one shot and stuff. So we put together a very detailed plan. You drone to fly this, so it was really important with the drone. We were able to fly and develop plans and cross sections based on the imagery from the drone. And understand this is a trim shot or a cushion shot, different from a pre, and that we didn't want any explosives riding downhill and popping in the air or popping on the muck pile. And so once we came up with a concept, Jerry worked with Thomas Palou in our office to develop the models for the cross sections and stuff for loading and shooting this rock mass itself. So we're looking at about 14,000 cubic yards of rock. This required about 7 days of drilling. We had about 130 holes. These holes are atypical because they were 100 feet deep. Some of them 100 feet deep, and some of them were at angles of about 55 degrees, which is really difficult drilling in these type of conditions. So we had a crew on site drilling. We had some people from McMillen Jacobs up there monitoring as logging holes as they drilled, and we'd spend like 10 to 14 hours a day drilling these holes. But it was quite amazing. We got about 7,000 feet of hole drilled in about 7 days. It took a day to load, and loaded about 6,000 pounds of explosive. All right, just a typical cross section on the left, the typical blast hole. You'll notice we got a primer in the bottom, primer in the middle. We wanted to make sure that this thing shot, and so we loaded the hole such that's based on Jerry and I look at it. We talk back and forth. So, okay, let's load it this way. On the right, you'll see the typical production holes. Those are subvertical holes, and then you'll see that the trim blast hole or the cushion blast hole that's sub-parallel to the blasting or to the slide plane. So what we wanted to do is be able to shoot and lift us off of the rock mass or that slide plane, let it slide down into that catchment zone that we have created at the bottom of the slope. So on your left, you'll see we're drilling that 55-degree cushion blast hole. Now this is a difficult hole not only to drill, but it's really difficult to load too and such. On the right, you see Jerry and crew loading holes. You'll notice Jerry and Ethan off, we're right on the edge there. It's about 250 feet down to the floor. What we did, we had two crews loading, one loading the production holes. You can see Alexis there logging those holes. Carol Ravano logging holes for the cushion blast that's just off the picture behind us.
After all this talk about blasting, we should go ahead and watch the video. So you can see the berm was in place to help contain material. DEA was out. And McMillen Jacobs took drone footage. So this is from DEA.
We also brought a band with us.
One thing to keep in mind and keep fresh in your memory is the dust in that video. We'll talk a little bit more about air monitoring later on in the presentation. This project was unique because it had a $10,000 a day incentive to open 95. And Scarcella was able to open the road in 5 days in time for Labor Day weekend, so they didn't have any impacts to traffic over that weekend.
So one of the key things you'll notice that, well, first of all, this was a very technical shot, and thanks to Jerry's guidance and stuff on there, we didn't no rocks in the river, planted in the ditch and on the shoe fly itself. In fact, we got very few rocks even on the in those tree lines there. So it was a very, very, very technical shot, but it was basically a perfect shot too. So what happens now is after a shot like this, you've got to let the rock relax because the rock has been under a lot of stress, and so you just relieve the stress. So we let it rest and relax for at least 2 days. Once the 2 days were up, we got scaling crews immediately in. Now it was rock supremacy with Scarcella Brothers up on the slope. We got a crew in there up on ropes, also evaluating the stability of the slope, looking for areas that we needed to further shoot or clean off. We also identified areas to put in the rock anchors and such. In the meantime, we had Scarcella moving to open that shoe fly down there on the bottom. Now, scaling is inherently a very dangerous job. And these scalers typically are on ropes, are using scaler bars or pressure washing or pneumatic pillows to bring the blocks down. that's Ethan Guzik there. He's watching one of their blocks come down. You'll see that that ditch works perfectly. You know, just about 98% of our rocks will be kicked down when we're scaling stood within the in that catchment ditch themselves. And so that's what's really important, to have a good catchment ditch at the toe of your slope. Now, the drilling is done by a wagon drill. These wagon drills are lowered on cables, and you'll have an operator, you have a driller and then an assistant that's actually drilling the holes. So we're drilling the holes on the left. On the right, we're actually installing the rock anchors. These rock anchors, number 10 bar, weigh about 100 pounds a piece because they're about 20 long. Incidentally, we actually put in some 30-footers, so you can imagine the angst trying to get a 30-foot down there. Fortunately, we used a coupler to do that. But it's a very dangerous job hanging on these wagon drills. But that's the way you do it. So where are we? So far, we're done scaling now. We've scaled about 1,000 yards of rock. We've actually drilled and installed over a mile of rock anchors. This includes the dowels, some rock bolts, and then also rock anchors for the upcoming drapes and techo mesh. We've installed about 300 linear feet of drains so we can reduce that hydrostatic pressure that's on behind the blocks, behind the main block. We're getting prepared to fly a mission with a helicopter to install about 60,000 square feet of wire drape on the south end. And right now we're installing about 2,000 square feet of techo mesh at the mouth of that chute. And the reason we're doing that is we discovered at the top we had these fluvial boulders, or alluvial river type boulders, that apparently were laid down many years ago when the river was higher in the valley. So we've got erosion, say 250 feet. And so this is a ancestral type riverbed. And these rocks are so rounded and they just go down like bowling balls down the slope. Presently, Scarcella is moving the berm. By the time they're done, they'll be moved about 35,000 cubic yards of rock. And then we'll start repairing the road itself in about 2 weeks, and we'll be installing a T35 type Rockfall fence right at the mouth of the chute as additional protection.
So one thing I wanted to take the opportunity to raise awareness about that we encountered on this project is naturally occurring asbestos. Cody Stevens is a PhD student at the University of Idaho. He shared his thesis with us. He saw the slide on the news and let us know that his analysis had shown that there was naturally occurring asbestos as part of the rock of the slide. And most folks, when they hear asbestos, they think of building materials. And there are some ways that they're similar, but there are some very key ways that it's different, that you need subject matter experts in the mineral form of asbestos, which we'll talk about a little bit more later on. But one thing I want you to keep in mind is that OSHA requirements apply for naturally occurring asbestos and projects in construction as well. And they have 3 different classifications: none detected, less than 1%, and greater than 1%. And the key differences between those classifications are the extent of your monitoring, your training program, and how you can dispose of the material.
You know, one of the key things you understand, asbestos is just a general term. It applies to a lot of fiber type minerals. Typically, in this case, in naturally occurring asbestos, we're dealing with actinolite or trinolite. And with the serpentinite, that greenstone that Jim was sampling, that's typically actinolite. But also there's other fibrous type minerals like tigerite that's not regulated, but you should really treat because of the fibrous nature by still using dust control methods, and when drilling using half-face respirators and such. But you'll notice that greenstone on the right is pretty massive, but which is important. I'll talk about that in a minute. The sample on the left, that inset photo, is actually along a shear zone, which is antigerite, which is a non-regulated type fibrous mineral. It looks just like asbestos. When I first got into it, I said, oh boy, here it is. And then we got with our subject matter expert, Dr. Hurston, and he said, "Oh yeah, that's antigerite." I said, "Oh, no kidding." And with that,
Yeah, so one thing, like Bill mentioned, having that subject matter expert, we initially, the department had samples sent to a lab that was qualified through OSHA regulations to test for asbestos, but they were not familiar with naturally occurring asbestos. So they tested those samples as if they were tile using an ignition method, which gave us incorrect results. And so it's really important to work with subject matter experts who are familiar with the mineral form of asbestos so that you can move forward in the right direction.
So one of the key things is setting up our sampling protocol. So basically we stopped everything and said, okay, we're going to have to go out and sample and see what the story is here. Now we were under the assumption, and Bradley Hurston said that's true, that these massive chunks of serpentinite and stuff probably don't have the asbestos. We assumed that the asbestos type minerals would be along the shear zones, and so we set up a sampling protocol. Initially, we were taking seven locations, 3 samples each, so we could test a full suite of samples and then compare them to the next set samples and such to see if we're getting similar results. But the key thing is that we wanted to get that big block up there in the top out of there. And we were concerned that if indeed we had naturally occurring asbestos in this block, we're going to have to go through a total different set of protocol methods to bring that thing down. And so we changed our testing protocol. Said, okay, test these first, because this is a massive chunk of serpentinite sitting on top of the wedge there. And we found that our suspicions were true. These were non-detect. There's no asbestos type minerals in those test samples, which was good. So we could bring that rock down under using normal methods, understanding that the drillers would be using face masks as they drill, and we still control the dust and such. Now, you'll notice that there's a big gap in the center. Well, there's a reason for that is it's a very dangerous area there. It was about, we'd have to come down about 200 and some feet to sample that area. It was all broken up. And said, so Jim Strother and I said, okay, well, let's look at this. We'll sample the shear zone. So you'll see location 3 and location 4. Those are right along the upper shear zone. In fact, location 4 is where we found the antigerite. And then location 5 and 6 is along the lower shear zone. Now we did find actinolite, but it was basically either non-detect or less than 1% in samples in 5. And over in sample 6, we found one sample that had 5% actinolite, asbestos type mineral. You can see that shear zone that goes along there, but fortunately, where that location is, sample 6 area, we could isolate that. We weren't going to be doing any digging there or actually there. It's going to be covered by a rock mesh we'll talk about later. So we just totally avoided that area.
So like Bill said, kind of the key thing that we were able to do by taking this rigorous sampling and really characterizing the slope was to avoid disturbance of areas that had greater than 1%. That's the first thing that we did with the contract. And in areas that we couldn't avoid disturbance, we used wet methods to manage the dust from the project. One thing that we did with the project that was unique was perimeter air monitoring. This isn't required in Idaho, but we worked with our subject matter expert out of California and kind of used their regulations just to set up specifications and protocols to make sure that we weren't exposing community members. You can see there's one on the picture. That's our air sampling locations. Number 1 is at the Night Forest Ranch. Number 2, there are some homes along the river. And because this is pretty new, at least to District 2, working with naturally occurring asbestos, we wanted to have good data about what methods were effective and make sure that we weren't exceeding OSHA limits or making sure that we were taking the appropriate measures. And then the last thing to mitigate was to make sure that all the staff working on the project and the contractor had the appropriate training. So all of our perimeter air data was less than 0.005 fibers per cubic centimeter for the July 8th blast and the 2 days following the cleanup when they moved the rock berm. We've taken perimeter air monitoring several times since then, and we're analyzing those results. During this initial blast, we also had, and cleanup, we had operators wear personal dosimeters, an excavator operator, a dozer operator, and a haul truck driver. And all of those results were less than 0.007 fibers per cubic centimeter, and that's all less than the OSHA permissible exposure limit. And the other piece that we weren't sure if it was going to kill the project was disposal of naturally occurring asbestos. Unfortunately, we worked with property owners nearby. Night Forest Ranch there owns the property that we needed to access the top of the slope, and they were willing to be a waste site. And so instead of hauling to a waste site and risking exposure throughout that whole haul route, we were able to haul just to the north, waste material there, and encapsulate it at the end of the project with soil. I know we're running out of time, so I'll be really quick. So just an idea of the Pacific Northwest, the areas that the USGS has identified with naturally occurring asbestos. There are 8 locations in Idaho, and you can see our slide is not currently one of those locations. So just be aware, if the USGS hasn't identified it, it doesn't mean that it isn't there. There are 33 locations in Washington and 22 in Oregon. So it's something to look out for. It's not a project killer, but you need to take the appropriate measures so that you can do your project safely. I wanted to take the opportunity to thank Megan Saucer and all the folks who collaborated with us to have successful communication. Given the daily changes in the conditions, especially at the beginning of the project, it was essential to communicate to make sure they knew so they could plan their trip and successfully travel the route.
So what do we learn? What do we conclude? Well, the slope is stable. Typically, when you mitigate rockfall and stuff like this, you shoot for 90%. You know, you don't want to tell the public or anybody that you've got 100% containment, because you're opening up yourself for a lawsuit when the first rock flies down and misses your barrier. The second thing is you're never going to get to 100% anyway. You're going to have to expect, as the slope equilibrates over time, you're still going to have some rattling of small rock and such. That is typical.
So as Bill talked about, using a drone was really essential. It gave us more than just great footage for our presentation. It helped us communicate, develop the blasting plan, the doweling plan, so that we could share those images with the subs, the prime here in the office, to make sure we're all on the same page about the scope of work. It also gives you the opportunity to assess and analyze areas that are unsafe to access by other means.
Yeah, you know, spending $60,000 on telemetry was very well worth the money. We were very concerned about that block moving without us controlling the movement, and so that was key. And plus, we learned a lot about the rock and stuff itself just by following this telemetry and stuff. And you'll notice we have a really clean slope up there. Got a lot different than it was back 4 months ago.
And then just wanted to give one more reminder for folks looking out for naturally occurring asbestos. Get with your geologist, have them assess the slope. Once you understand the risk, work and get together the specifications, have them in your contract. Naturally occurring asbestos isn't a project killer, but it's something you need to be aware of and take appropriate safety precautions.
One of the things is if you see greenstones, they're suspect for your asbestos type rock in a metamorphic terrain. In fact, in Northern California, if you got greenstones on the project, you automatically assume that you have naturally occurring asbestos and you have to prove otherwise.
So just as we're wrapping up, I wanted to thank the core construction team. We couldn't have done it without you. There are a lot of people who worked on the project and worked long nights and evenings and weekends, and so thank you so much for your hard work. And so with that, maybe a famous photo of the slide. I want to say thank you for your time, and have our contact information listed here, and we have just a few minutes for questions, and so you can reach out to us with questions if we run out of time. Thank you.
Thank you so much, Janet and Bill. If anyone has any questions, please type them in the chat box now, or go ahead and mute yourself at this time.
This is Daniel Jorno. I had a question for Bill. You mentioned the movement from the heat. I was wondering what kind of movement were you getting? And secondly, is the movement an effect of surface area or surface area and thickness?
Hi, Daniel.
Hi.
Yeah, the primarily what we were noticing is there was a movement because of heat, because it would basically expand, and you had this the surface area of the rock there. You know, a couple of days it got up to 105 degrees there and stuff, and we could definitely see as during the diurnal changes around when it was the hottest, we'd have the most movement. We're only talking, you know, a couple thousandths of a foot. But, you know, when you put that on the graph and you don't put a scale on it, you say, oh boy, we got lots of movement. But really, you didn't have much movement at all. But it was still, it still contracted. So it's pretty interesting.
Is that a function of the surface area and thickness, or just surface area and color of the rock?
I don't think the thickness has much to do with it as much as just the surface area there that was heating up and stuff, and probably right close to the crack gauges.
Thanks, Bill.
Any last questions? All right, then. Again, thank you so much, Janet and Bill. Great presentation. If you would like a PDH, please type your name and your email in the chat box here below. And just an FYI, we did have this presentation recorded, so we will be sharing this recording with ITE and on our ASCE webpage. Thank you again so much for coming, everyone, and hopefully we will see you next meeting.
Thanks, Lauren.
Thanks a lot.
Thank you.